So our second speaker today is Dr. Neel Gala from InCore Semiconductors PVT Limited, based in India. Neel is the CTO of InCore, which is an early stage fabless startup. InCore is one of the leading providers of silicon-proven RISC-V processors in India. Received his PhD in computer science from IIT-Madras, one of the top universities in India, in 2016, and is also one of the creators of the SHAKTI Program, initiated at IIT-Madras in 2012, and was the lead architect of India's first indigenously designed 64-bit RISC-V chip, codenamed RISECREEK. Neel also serves as vice chair of the compliance test group of RISC-V International. He has published more than 20 international articles and is an avid open source contributor and promoter. And the title of his talk today is RISC-V Verification Generators, a configurable ISE warrants a configurable verification environment. Over to you. Thanks, Neel.
Thanks, Mark, for the kind introduction. Good day to everyone. So InCore is primarily focused on building RISC-V core IPs. As part of that, we tend to do a lot of verification around it, and we've grown to use a lot of open source tools and environments to enable that. We obviously appreciate the fact that sign-off needs to happen with commercial tools, but you can complete 80% of the leg using open source tools and languages. And this talk is primarily aimed at what we do at InCore and how we bridge the gap as an early stage startup, where verification can definitely become bottleneck both financially and on the tech side as well. So let's get started. If you look at the modern trends of computing, even for things like domain-specific accelerators, composable computing, chiplets, disaggregated architectures, and what you would realize is a configurable ISA like RISC-V, which is open, flexible, more importantly modular, has a higher potential or higher confidence of success in realizing the next generation of solutions. Right. And the fact that there exists a rich and diverse ecosystem already, both in open source and commercial environments, it sort of plays a key role in making sure that RISC-V survives the next computing wave that's about to come. Right. On the other side, if you look at how people are now building processors or building cores, you see that there's a good amount of adoption of high-level languages like BlueStacks, Chisel, Spinal HTL, and so on, where the designers are able to invite the same amount of parameterization and configurability as typical software engineers would, right? So what's happening now is you're shifting from folks developing a static code with a static configuration to actually building a single piece of code which can generate multiple instances, hundreds if not thousands from the same piece of code. And that's where the configurability of microarchitecture and ISA at the design level has started creeping in. Right, so you're not getting cores anymore. What you're getting is code generators, right? Even if you do not believe in the idea of code generators, as Simon previously mentioned, everyone is a microarchitecture licensee, right? Everyone wants to build their own microarchitectures. There is just going to be a huge amount of fragmented and discrete, unique RISC-V cores out there, which stand apart but still are RISC-V compatible. Take these two ideas, put them on the table. You have a configurable ISA on one side and you have discrete and configurable cores on the other side. The problem on the table now is verification. How do you build a verification environment which targets all of this configurability and avoids you to going through a massive round of verification for each instance that's possible in the RISC-V world, right? And that's what this talk is about. I believe very strongly that a configurable ISA and a configurable core requires a configurable verification, where if there is a quantum delta that is applied to developing or configuring a core, there should be a proportional quantum of delta that happens in the verification where it should never be a restart of events. There has to be maximum reuse, and there has to be a huge amount of automation. And the talk is mostly going to revolve about using open source languages like Python as the basis for developing scripts, tools, and other open source tools, which will help you get through, 3/4 of the leg of doing verification. Maybe the sign-offs will require you to go a little more advanced, but you can get a very robust and a very stable IP by adopting some of the solutions that I'll be talking about today. Just a quick note, considering the short length of the talk, I will only be putting out the challenges and the outcomes and some certain solutions and pointers to solutions. The discussions of each of them will obviously require a much longer forum, but I'll be happy to discuss them with you offline, and feel free to reach out to me at any point. So for me, I break the whole verification environment into 3, if not 4 different components. It starts with a test harness or a test bench of sorts, which indicates, what's the interface of the DUT, how are you instantiating your reference model, how do you synchronize between them, are you doing log-based comparisons or a step-in compare and whatnot. We then move on to the test generation aspect. What are the different ways and different types of tests that you need to create in order to truly verify your code. And then the test coverage, how do you collect metrics which tell you that your test suite is worth it. It actually is quite advanced in covering both the ISA spec and the functional coverage of the code. And finally, I'll be presenting what InCore has developed as DevelopCore along with Solve, which is sort of an integration framework which can bring all the first three steps under a single umbrella framework. So let's dive into it quickly. This is something similar to what Simon presented. At a very high level, this is what a RISC-V verification would typically involve, a RISC-V code verification would typically involve. You start with an assembly program. This could either be a single test or it could be selected from a pool of tests. You can use conventional compilers like GCC or LLVM or a custom SDK of your choice to compile the test, create a binary. You feed the binary into a DUT, that's it, and you feed it to a reference model, right? They both produce results. You compare the results. If they match, you declare that the test has passed, else you go figure out what the bug was, right? Well, this all looks very simple. There are a few caveats that come into the picture, right? The reference model, for example, SAIL or Spike or Impressive Simulator or Whisper, anything that you pick up, the main goal is to mimic the DUT as much close as possible. Right now, remember the DUT itself is configurable or can be any one of the commercially available cores out there. And you cannot have an equal number of reference models. You would rather like to have a more configurable model, right? And this configurability can either be, inherited at build time, for example, how SAIL does it, or it could be via a command line interface like Spike. What is more, one good thing that could help in making it more configurable is if you had a standard specification format which could say that this is how a DUT is specified in the RISC-V world. And InCore, along with Empress, we worked together a couple of years back and we came up with the idea of RISC-V config, which is now also adopted by the RISC-V Foundation as it's basically a YAML format which allows you to define all the choices that a particular DUT has made with respect to ISA and platforms and defined by the RISC-V spec, right? If I have that information in a standard way, it becomes sort of easy for me to build and configure a reference model which mimics the DUT as close as possible, right? The reference models obviously have to be proven. They should be either community accepted through empirical data. If there are 1 million users, you're sure that there's a higher chance of stability, or someone like RISC-V Foundation has put a stamp saying, SAIL is the golden model and it will be referred to as. There are other options, Whisper and other simulators, which can also be used as a reference model as well. But the configurability of the reference model is where the configurability of the test environment also comes in, right? If your harness is able to cope with the changes in the DUT by adjusting the reference model either through CLI, that's how you can scale up pretty fast, right? So you need to spend time there. On the comparison side, the idea is to check if the architectural changes that are occurring because of execution of the test, are they the same on the DUT and the reference model? right? And you can do them in two broad ways. There's a log-based mechanism and there's a step and compare mechanism. We'll quickly look into the differences next. In the log-based, the flow is pretty much the same, except after the end of execution of a test, the DUT and the reference model both generate a log file. This log file basically includes, for every instruction, what is the change in state that occurred. It could be a register change, an MD change, a CSR change. If these two files match, then the test has passed, right? You could also do signature dumping. You could say, along with instruction execution, I also want to check at the end of the test a certain memory region, do they match or not, just to increase more confidence. Now, this is definitely easy to set up. It requires minimal scripts, Linux-based or Bash scripts, quite easy to build for this. And in no way this affects your simulation times, right? So whatever you can run your DUT, RTL simulators on model sim, on Verilator, it's not going to get affected by this. There are some downsides. For example, the log size for large tests can become really big, hundreds of GBs, and doing a diff or doing a comparison at that level can take significantly longer. Failures are difficult to debug because even an early failure would require the test to end completely, only then you can go and figure out what's happening. And with the minimal amount of information in the log files, debugging can become quite difficult. There are a few kinds of tests which depend on the uncore aspects of RISC-V. For example, counters, timers, interrupts. Because you will be using an instruction set simulator like Spike, which is delay insensitive as compared to a cycle accurate DUT model, certain kinds of tests are not suitable for a log-based comparison method. But for that, we have things like step and compare mechanisms. The idea is simple, but it's slightly more complicated when you implement it. The concept is basically once you have a single binary, instead of running them independently on the DUT and the reference model, you sort of step through every instruction and you synchronize between the DUT and the reference model. So you take the first instruction, you wait for the DUT to completely execute it, and then you halt the DUT. You then indicate Spike or the reference model that you need to execute the same instruction, and then you compare the states at that point. If all the architectural states, you could choose to compare all registers, a few registers, or only certain architectural states of interest, depending on what you're debugging or what you're executing. If the architectural states match, you redo the thing and execute the next instruction and so on. So you're basically stepping through the program and you're comparing the architectural state at every instance. Now, obviously, it becomes very easy to debug failures because you're going to stop instantly as soon as you detect the failure, and you can do a down, save, restore sort of mechanism. Delay-sensitive tests, for example, interrupts, can also be used to make sure that the reference model is in sync, or any uncore event happening on the DUT side is communicated to the reference model through a synchronization routine. The cons are definitely slow simulation speeds. Now, there's a DUT, there's a reference model, there's a synchronization happening. All of this obviously is now going to consume a lot more time. The reference model will definitely have to be wrapped in an API, will have to be massaged so that it can be dynamically changed, its states can be updated, its states can be read. Definitely a more complex setup than the log-based, and the language in which you develop the environment, whether it's system Verilog or Python or Verilog or VHDL of your choice, the capabilities that you can grow will definitely be impacted by the language of choice. You'll have to work around either too much, or you could really scale up very well if you use languages like Python as well. So at InCore, we've taken a stab at doing this using an environment called CocoaDB. CocoaDB is a library for digital logic verification in Python. It's completely open source, it's completely free. And more importantly, it basically gives you a Python interface to RTL simulators, and it's agnostic of the simulators themselves. So we use Verilator underlying below CocoaDB. And in CocoaDB, we sort of define the test bench. That's the diagram that you see. It's a conceptual diagram. Very similar to what you would typically see in a UVM sort of an environment where you have the RISC-V core on top, you have the reference model at the bottom, you have the input and output monitors, and then you have coroutines. Coroutines are basically threads or background threads that happen in Python through CocoaDB. What these coroutines do is they make sure that any uncore event, for example, if there is there's an interrupt detected at the core, the same interrupt is communicated to Spike at the relevant architectural state, right? So these coroutines are responsible to make sure that the core and the Spike and the reference model are at a similar architectural stage due to uncore events, right? And you have a scoreboard mechanism And CocoaDB gives you these libraries and APIs. You don't have to build a scoreboard from scratch, or you can have very simple scoreboards. A lot of the DPI mechanisms or communication with the simulators or the RTL, all of that is done in the background, so you don't have to suffer much. In our attempt to getting this up, I think getting Spike here was a small bump in the journey, where we sort of said, we had to take the C, we had to write a wrapper around Spike, which can instantiate it, which can read the registers, and then that API was in C. We had to read it in Python using something called Swig. It's all automated, but going through the journey, we realized even reference simulators or reference marriage will have to undergo changes in order to really mimic and synchronize in such an environment. But there are definite pros to here in such a step and compare, where large simulations, if you're doing something like Linux, log-based mechanisms will definitely not work, and especially deep down in the simulation times, step and compare of this sort of an environment works out really well. Okay, so running short of time, the next target is about test generation. You sort of want to focus on automated test generation rather than doing it manually. And instead of taking on the whole idea of test generation as a single problem, we sort of split it into 3 categories. We have compliance tests at the beginning, which ensure that you have implemented the ISA spec correctly. If a software which mimics this, is according to the spec, it should run functionally well on your system, on your code, but that's not bug-free. So it acts as a good smoke screen. And then there are random tests, which will help you improve the initial confidence, because they sort of generate a wide variety of random corner cases, both in the ISA and microarchitectural space. And you can quickly increase your coverage by using random tests or nightly schedules in order to get there. Finally, microarchitects, you definitely want to spend a lot of time here. And the idea here is to hit that functional coverage to the last one in order to claim as close as possible to being bug-free. InCore has developed a lot of tools with regards to test generation. The first one is the compliance test generator or the compatibility test generator. It's more of a coverage-driven test generator, where the cover points are defined in terms of ISA architectural states. You define whether I want an add operation, where all the operands are different, where one of the operands is the same as X0, or 2 of the operands are the same, and so on, right? And CTG basically picks this up, uses the constraint random solver, figures out a solution, and dumps out an assembly program, right? And it has tons of new features, tons of fancy features. We've been participating with the Linux Foundation's internship program, and constantly adding newer features to this. And this is where compatibility with the ISA can help you a lot. Random tests, I think, sure shot, APG is one of the best random program generators out there. It's extremely feature rich. You can configure the kind of flavors and distribution of instructions you want to use, what sort of memory, behaviors you want to see in the test. You want to have custom snippets. APG will help you cover a lot of ground very quickly with a high amount of stability as well. We've also created a tool called UATG, which stands for Microarchitectural Test Generator. Instead of parameterizing assembly programs, we sort of raise the level to Python, and we parameterize Python code, Python plugins to generate assembly programs, right? And these plugins basically receive configurations from RISC-V config or core config from a particular core, and therefore are able to tune the generated assembly as per the choices made by the DUT. There is also a tool called ISA coverage, RISC-V ISAC, that InCore has developed and adopted by the RISC-V Foundation. The best part is this tells you how much of the ISA have you covered using your tests. The good part is you don't need to do DUT or RTL simulations. You can run these on a reference simulator only, pass the logs, and it will sort of tell you how much of the spec has been covered or not, right? It's extremely fast, it's parallel, it supports Sales, Spike, all ratified extensions, and a lot of cool features available, and there's the link for you guys to check it out. Lastly, there's functional coverage is always the problem. To add configurability, the reasons you want to do that is with languages like high-level, Bluespark or Fizzle, the signal names can start changing quite drastically and quite quickly. So you need an aliasing YAML, where you define all the cover points based on alias names. And if your design changes, it's only the YAML that changes. It's only the aliasing change. The cover points or the code or properties do not change. certain signals, cover points only exist under certain configurations, and you sort of want to leverage Python over there to select these filters. Right.
Hi, Neel, we need to wrap it up here, please.
Yeah, I'm on the last slide. Sorry for the delay. Yeah, and finally we have River Core. This was also developed along with the Solve. This sort of integrates different APIs together, sort of give you a single-stop solution for test generation, simulations, reference model comparisons, and so on. Apologies for the delay, but thank you for listening.
Okay, thank you very much, Neel. Unfortunately, we don't have time for questions. So if there are any questions, please email them in and we'll pass them on to Neel. And the other point to make here is that our first DV Club talk next year is on Python and CocoaDB. So that fits quite well with Neel's talk. Okay. Thank you very much, Neel. Thank you.
Thank you, Neel. Appreciate that. Just to pick up on Mike's point,